get started. Let me my video. Hello, everyone. Hello, Ryan. Hi, hello, Eyone. Nice to see you guys. And
Hi.
hello, Lebohang. And I believe the other person on the call is Ali and Fatima. Thank you so much for joining us today. I'm very excited for this session because this is a group of people that I've had the pleasure to work with. So I'm happy that we're going to present some of the work that we've been busy with and we hope to take forward. So the live session today is on mapping flood extent using Sentinel-1. It'll have two components to it. The first one being what you're probably used to if you've attended the Digital Earth Africa live sessions, which is a notebook that we have on the platform that will take you through, but also something very special that we started working on at the Sarao Big Data School, where we all met and were part of one group called Aqua 6. 6 people. So it was Ryan, Eyone, Gloria, Rebecca, Philippe, and Osbone. Unfortunately, Gloria and Rebecca are not able to join us today, but we do have Ryan and Eyone to take us through the presentation as well as myself. And we'll have another presentation in French with Philippe in the following week and in Portuguese with Osbone the next week. So I'll just do the basics introducing Digital Earth Africa. So for those who are not aware, Digital Earth Africa is based on the premise that we want to provide a public infrastructure and accessible analytics to unlock the power or the value of Earth observations. And we're doing that for all countries in Africa. So we're empowering countries across Africa with Earth observation data to enable climate adaptation, mitigation, and greater food security and more sustainable development. This is a program that is based on the Open Data Cube infrastructure and is supported by Amazon Web Services, which hosts the data and also provides us with an analytics platform, which is called Sandbox, that we use to do analysis. So everything that we offer at Digital Earth Africa is completely free, even for commercial use, and everything is optimized for web processing, and we offer complete visibility from the data to the product. And we have different interfaces that support the needs of different users and an extensive library of SDG-oriented tools, as well as giving you an analysis platform that allows you to build complex analyses on your own topics in your own environment. And we rely on satellite imagery that is freely available. So we're looking at Sentinel from ESA, as well as Landsat from the USGS. And we also create products on top of those readily available data sets that we provide at analysis ready level. But this is all available through the Digital Earth Africa platform that you can check out and see what is available through the platform. I will stop here and hand over to Eyone to introduce to us the team and as well as how this team came about. So Eyone, over to you. Eyone, are you there?
Hello, yes, Mpho, I'm here. Good afternoon, everyone. My name is Eyone Sese, and I am a student at the University of Forte. I am proud to be part of the Aqua 6 team that was formed at the Big Data Africa School. So before we begin, I would like to quickly tell you about the Big Data Africa School. So the Big Data Africa School is an initiative that brings together students from different backgrounds across the continent to develop data-driven solutions to real-world problems. So this year it was held in Cape Town from the 10th to the 15th of March. And this year's theme was the application of machine and deep learning to Earth observation data in solving African challenges. And there were 5 projects that students were working on. First one being crop mapping, the second one being strengthening weather prediction capabilities, the third one being mapping and monitoring peatland and mangroves in Africa, the fourth one mapping and monitoring urban development, and the fifth one being mapping flood extent, which is the one my team and I have been working on. May I please go to the next slide? So in this session, the Digital Earth Africa will demonstrate the use of Sentinel-1 data to map floods and the impact they have on livelihoods. So Sentinel-1 has the advantage of seeing through clouds in tropical areas, and it is more suitable for mapping impacts of floods as they occur. So my team and I, which I will be showing on the next slide. Can I please see the next slide? So this is the team that made this project a success. We have Philippe from Madagascar, Gloria from SA, Osbone from Mozambique, Ryan from Namibia, Rebecca from Ghana, and myself from South Africa. So floods are amongst the most devastating natural disasters which affect millions worldwide each year, and Africa is no exception. So they cause loss of lives, the destruction of infrastructure, displacement of communities, and economic losses. So these consequences are not just environmental, they are economic and they deeply affect humans. So Earth observation, for example, the Sentinel-1 enables fast, large-scale flood detection even in bad weather. So response is often delayed to address floods. This is due to the lack of real-time data. So to address this, we need accurate data, we need wide-scale data, and this is where Sentinel-1 comes in. So Sentinel-1 is equipped with synthetic aperture radar, which allows us to see through clouds and rain, and it can also capture data during the day and night. It has high resolution and its data is freely available, which makes it ideal for our project. Next slide, please. So these pictures show the impact that floods have in our communities, on our lives and the infrastructure. The first picture showing how floods can damage the infrastructure, the road is damaged. The second one shows how people are affected, their houses are underwater, their daily lives are affected. So this highlights that as these infrastructure are damaged, it may take millions to repair this infrastructure. So that's how we show that floods not only affect the economy, but they also affect people and their livelihoods as a whole. So now I will hand over to my colleague Ryan to take you through our flood extent mapping notebook. Thank you.
Thank you, Yona. As previously mentioned, I am Ryan, and I'll be taking you through the flood extent mapping. I'm from Namibia, and I represent NUST, Namibian University of Science and Technology. So for our study, we actually adopted a quite systematic approach, whereby we used, as mentioned, the Sentinel-1 data. In this case, we started off with selecting our location in the time range, then loading our data, converting the digital numbers to decimal values for analysis. We created our median VH and VV polarization composite images from the data, then followed by K-means clustering and showing the urbanization K-means clustering for the predicted image, as well as ground truth to reflect and look at the accuracy of our analysis. And then comparing the urbanization prediction with the ground truth, and then ending it off with water change detection. Especially when doing flood risk mapping. So in this case, our study area was Beira. As previously mentioned, our team consisted of someone that's located in Mozambique, in this case, Beira. So during the time, we used the time range from February 2019 to April 2019 as indicated. This was also, if I'm not wrong, this was also around the time of the cyclone Idai, if I'm not mistaken. So therefore also capturing the aftermath of this cyclone. Can you go to the next slide, ma'am? So then for converting the digital numbers to decibel values, the raw digital numbers were converted. This allows us to enhance our interpretability. As converting it allows us to visualize and interpret the subtle differences that can be seen on the features such as water, as well as vegetation in urban areas. For generating our median VH and VV polarization composite image from the data, so we had to create a median composite of this. So what does VV mean and what does VH mean? VV typically means that there's a vertical transmission as well as vertical receive. And then VH means there's a vertical transmit but horizontal receive. Therefore, the radar signal is sent and received in vertical polarizations, whereby as the VH allows signal to be sent in a vertical and received in a horizontal polarization. So the median composite of this VH and VV bands, it's generated to allow us to reduce noise and highlight consistent surface features over time. Therefore, it also allows us to reduce speckle noise, which is quite common in our radar image. It also allows us to remove outliers that may be caused by temporary changes such as sensor anomalies. Next slide, ma'am. So during this generation of a median, we also had to do our threshold determination, allowing us to benchmark where we're gonna use, what value we're gonna use to separate water from non-water. In this case, looking at the histogram diagram or the backscatter distribution diagram of the pre and post flood images, in this case, the right peak indicates higher decibel values, also representing that there's non-water. And then on the right side, we have higher decibel values representing non-water. On the left side, we have lower decibel values, with the blue representing pre-flood and then the cream representing post-flood. So then, using this distribution, the minimum point between the two peaks, this is where we will use or establish our optimal threshold, therefore allowing us to have a specific threshold to separate the water and non-water. So looking at this, the threshold is close to negative 16.3 around that average. Therefore, with that said, backscatter values lower than negative 16 are typically classified as water, whereby as opposed to backscatter values higher than negative 16 are classified as non-water. Now this can be buildings, vegetation, and soil. Okay, just the next slide. So even with that, now we separated both our classes into water and non-water, right? But now we can determine effectively where areas have been flooded. So basically now the next step was to do a change detection, whereby we basically used the post, which is the red in this case, subtracting it from the pre. Next slide, ma'am. In this case, it allowed us to effectively see and analyze the area on where the water change has happened. The water extent has happened. In this case, blue is classified as water to water, therefore a constant in the water body, with yellow representing water to no water, and pink or purple, lightish, we have no water to water. Therefore, we have a sense of where the areas are that's flooded in this case. Next, we did unsupervised classification. The K means clustering. So we use the ESA, which is the European Space Agency data set. In this case, we can see that they have several classes there, but our main focus will be on the built-up areas and of course the water. So using this data set, we implemented, not this data set, but we use k-means clustering, and then using this data set, we validated our data. So for the next slide. So using the k-means clustering, we classified our data. In this case, we have our urban areas on the right using our k-means clustering and reflecting it with the ESA dataset. In this case, I'm pleased to say that or report that our urban areas have been classified with an overall accuracy of 84%. Now, looking at this, we can see that there's quite a higher level of accuracy compared, not a higher level, but there's a relevant higher level of accuracy compared with the reference data set we used. So using that as well, the next slide, ma'am. Using the ESA dataset, we could also see that we did our vulnerability map. Now, we classified our classes with red being urban areas, green being the vegetation, blue the water to water, and the yellow with pink being water to no water and pink no water to water. Yellow being water to no water, this can highlight a sense of evaporation might have taken place or small drought phase happening. And then no water to water, this is where the areas have been flooded. Then the next slide. Now using that data set, we did our flood-prone mapping. In this case, the red indicates the high susceptibility of the urban areas. So therefore, high flood-prone to built-up areas. We can see that there's a high concentration towards the south, as well as on the north of the map, with high flood-prone to croplands, indicated with a yellow color. And then I'm quite sure there's a sense of little bit of medium as well as unaffected areas, but it's relatively small in this case. So therefore, more emphasis on the high flood prone to built up areas and croplands. Thank you. Then I'll be handing over to my colleague for the deep learning solution.
My apologies for that. I couldn't find unmute button. So in addition to this great work that is possible through this thresholding approach, the brief for the project also mentioned leveraging deep convolution neural networks to do this classification, or to rather work on mapping flood extent. So as part of the data school, this team also went ahead and started looking at developing a deep convolutional neural network for flood mapping. And the reason that deep learning works is because the deep learning models are designed to understand relationships between pixels in an image. They analyze the surrounding context, which allows them to detect floods more accurately, even in more complex environments like urban areas, which in this case we're mostly interested in, or in areas that are vegetated or areas with mixed terrains. These more traditional thresholding methods can be sensitive to noise, such as changes in lighting or the surface reflectance, which can lead to false detections. But with deep learning models, it is a much more robust approach, and it learns the patterns from the data, which reduces the chances of false positives in being in clustered or noisy images. And one of the main advantages is that deep learning models automatically learn what features are important for detecting floods. Unlike thresholding approaches, which require predefined rules, or for you to go in and look at what that separation between the non-water and the water pixels is, it's just a much easier thing to work with. So that is what I will be presenting on. So for one thing to note is that within the Digital Earth Africa platform, we don't necessarily have any deep learning approaches. So this is kind of pioneering in a sense. It's a first stab at creating a workflow that uses a neural network, and we're hoping that it'll be one that we can share with everyone when it's ready. But yeah, just bear that in mind. This is literally a first crack within the Digital Earth Africa sandbox. And this is mostly specifically because the sandbox is restricted to CPUs, does not have GPUs, which can be quite restricting when you are working with neural networks. But we tried something and we have something to show you. So for that deep learning workflow, we use the SEN 111 floods dataset. So this is a carefully constructed dataset that is designed to train and evaluate deep learning models for flood detection, specifically for Sentinel-1 imagery. It was generated by Cloud2Street, which is a public benefit corporation, and it is widely used for both research and practical applications. The dataset covers real flood events from across the globe, collected from 15 countries, as we can see on that image there, with 3 countries being in Africa. So this variety ensures that the dataset's utility is diverse. It ensures the dataset's utility in diverse geographic regions and environment, because we're covering many parts of the globe. And one of the key advantages of the SEN1 plus 11 is that it uses Sentinel-1 image, which Eyone previously mentioned can penetrate clouds, which makes it perfect for monitoring floods, even during stormy weather or immediately after a cyclone. Each event in the dataset includes the pre and the post floods image, and this temporal data allows changes between the 2 periods, enabling us to actually detect the flood extents and the dynamics over time. And it includes, obviously, both flooded areas and non-flooded areas in urban areas, rural areas, agricultural areas, forested regions. So it's quite diverse in terms of its coverage. And it is frequently used to train and evaluate segmented models, such as fully convolutional neural networks and UNets, which are excellent at pixel level flood detection. So for the workflow, we did not just come up with something completely new. There is a workflow that the SEN1 Floods 11 team suggests, but obviously that workflow is not just easily translatable into the Digital Earth Africa platform. It took a lot of work actually to translate it into something remotely similar that could actually run within the Digital Earth Africa with the limited computing resource. And the reason for using the Digital Earth Africa platform, although it has limited resources, is because we want to leverage, once we've trained the model, leverage the data cube, and then consequently use the model to do flood predictions as with the existing time series data that exists upon the platform. So the model that we trained is a fully convolutional neural network, FCNN, and this is a model that is optimized for pixel level classification. So instead of classifying image as a whole, they analyze each pixel individually to determine whether it's flooded or not, making them ideal for flood mapping. And unlike traditional CNNs that use dense layers, they rely solely on convolutional layers. This allows them to preserve the spatial resolution of the input image, which is crucial for accurately detecting flood boundaries. And these FCNNs automatically learn complex spatial features from data such as flood boundaries, water patterns, and changes in land cover, enabling them to detect water spread over a variety of terrains. So one of the advantages of FCNNs is their ability to be fine-tuned for specific flood events or regions. So it makes them very adaptable to different geographic and climatic conditions without the need to rewrite the rules. And I won't actually share the full notebook because that would just be slides and slides of me showing pictures of code, but rather I will take you through what the workflow includes. Like I said, it's adapted from the SEN1 Floods 11 framework that they suggested, but it's customized to run within the Digital Earth Africa sandbox, which only supports CPUs. So we start with Sentinel-1 images and manually matched flood masks. if you can allow me to go back to the previous slide. This is the data that we have available, this graphic at the top here. So for each area, you get a Sentinel-1 image, a VV and a VH. If you wanted to use the Sentinel-2 as a component of the model, you could actually do that. But for this particular reason, for this particular endeavor, we're using just the Sentinel-1, so the VV and the VH, but we also have flood masks that are hand-labeled for those particular flood events. So that's what I'm referring to. So we also perform some minimal augmentation, mostly flipping and normalizing to help the generalization without actually doing too much heavy computation. The data is split into training, validation, and testing and it's split using CSVs from the source. So we use the CSVs to load those respective batches of data, which are the training, the validation, and the testing data. And the model is an FCN with a ResNet 50 backbone modified for a binary classification. And we train and track some key matrices such as accuracy and intersection over union to monitor the performance. And we then subsequently run the model on unseen test data to see how well it performs. So we trained this model on the full data set. So that's all 15 countries, all that data that we have available from SEN1 floods 11. And the training was only conducted for 10 cycles of 10 epochs each. So that's a total of 100 epochs to monitor the model stability, manage resource usage in the CPU-based Digital Earth Africa sandbox environment. So basically, we trained over 10 epochs with each epoch. That's the simplest way that I could explain it. And this allows us to balance the training time with the model performance. And we tracked a few matrices, which include the accuracy, which is the percentage of correctly classified pixels, which is useful for the overall trends. But I'll explain later, this could be slightly misleading as well. We also tracked the loss, which measures the error between the predicted and the actual values. It typically decreases over time as the model learns. And then we have the intersection over union, which measures how well predicted flood areas overlap with the ground truth. So those are those hand-labeled data, that hand-labeled data set that I mentioned earlier. And yeah, so as you can see here, I show you with this configuration, the model had a training accuracy of 0.8546, so that's about 85%, and the validation accuracy of about 80%. And when we track those matrices, it's you can quite see that maybe perhaps I should explain how to actually read these matrices that we tracked with the accuracy and the IO, the intersection over union. So the accuracy, we're looking at the orange for the training, the red for the validation. So it's these two lines, and the intersection over union are these two at the bottom. That at the top is the loss. So what we see with the accuracy and the intersection over union is that it typically starts low. So we can see it fluctuates, but it starts at around 20%, going as high as 60 in some of the instances, but it's pretty low. And we see the same for the intersection over union, but it does increase as the model as the learning progresses. And with the loss, this will start high. These are the two at the top, and we'll see it decrease as the model starts to learn. Obviously, we've only trained it for 10 epochs with basically 10 iterations. So it's not a lot of repetition that we did. So this model is not the best, but it is to showcase that it is actually possible to run a neural network within the Digital Earth Africa sandbox, and we hope to improve that. But we see that at the end, the training accuracy and the validation accuracy actually start to increase, and they're actually hovering above around 80 and 70%. That's why we have a final training accuracy of 85 and validation 80. But we see that the loss did not necessarily decrease as we would expect. It's still just below 70%. So what this means is that the model is making some good progress in learning to identify floods from the data that we've fed it as it's currently configured. However, the accuracy sort of plateaus and remains around that 80% mark. And this suggests that the model might not be fully capturing all the patterns in the data, and it has hit what we would call a performance ceiling. And this loss and the loss reduction is also slowed. As we can see, it's not exactly dropping to the lower values that we would expect. So the way we see it, there's further work that needs to be done. So the work that's related to hyper-tuning of the model, because currently this is just the first crack. We haven't actually taken the time to hyper-tune the model to assess things like the learning rate, the batch size, the optimizer. So this is something that we're going to be looking at in the future, and maybe increasing the epochs so that the model has more epochs to fully converge. Increasing the number of epochs could help the model basically improve its performance. But there's a lot of work that needs to go into that, and we will be looking at that. So in terms of the classification, this is an image from the SEN1 FLADS 11, such a mouthful, but yeah, SEN1 FLADS 11 paper that they wrote to accompany the data. So this is something that you would expect. You have your raw Sentinel-1 data, you have your hand labeled, and the CNN should technically be able to just improve on that hand labeled data set slightly. So this is what we expect for our model. Currently, what our model looks like, the accuracy is at about 80% for the test. This is a test on that unseen data. But the loss is still quite high, and the intersection over union could be better, obviously. But we do see that the model is, you could say in a way, it is able to capture those main patterns, but that still needs to be improved. And that goes into the configuration of the model. And that's something that we're going to work on and actually improve before we create a notebook that we can then share with everyone. We need to be certain that the configuration of our model actually works. And that's where these future work details come in. So we plan to redo a model, run it fully with the best configuration that we can achieve, leveraging GPU resources. Obviously, the sandbox doesn't have that, but I've had the idea to actually do it outside of the sandbox, but also leveraging data from the data cube. So this will also be another way for us to demonstrate how to use the Digital Earth Africa data outside of the sandbox environment, which will also be quite pioneering in making our data even more easily and available and accessible and usable outside of that slightly restricted sandbox environment. And of course, because we have that thresholding approach, which we're hoping this improves on, we want to compare it. And why not start with the Beira example that we looked at and see how that works, and then move forward with the rest of the work. And of course, we have some long-term goals to use the model for ongoing flood monitoring and early warning systems, and integrate these into national and regional platforms for real-time decision support for the entire continent, which aligns perfectly with the mandate of Digital Earth Africa. So basically, this is basically a response to a call to action. We want to save livelihoods. We want to support integrated watershed plan policy makers, and we want to reduce the risks that flooding disasters bring with them. So with that, that is the end of that presentation on flood mapping from Aqua 6, or in this case, considering only 3 of us are here, or 2 of us, or 2 of the team are here, Aqua 2. but the others will present in the subsequent weeks in Portuguese and French. But before I go, let me remind you that Digital Earth Africa has training courses that are self-paced, fully online in English and in French, with video tutorials, manuals, hands-on exercises, and you can get a certificate of completion for some of them. And if you want to connect with us, please do. We have our website. You can get in touch with the help desk, also the free learning courses, and these live sessions that we have every week in English and French, but also for this particular one in Portuguese. Please do join us on the other weeks as well. And thank you to the people who make it possible for Digital Earth Africa to operate. So thank you to our sponsors and our funders. And go Aqua 6, the best team. That's all from me. Thank you.